Do you ever wonder what happens under the hood when your Arduino does math? In this project, we're ditching C++ and doing it a different way, using pure AVR assembly to add, subtract, multiply, and divide right on an Arduino Uno. Before we get started, do not forget to like the video and subscribe for more content. You'll also find a link to the GitHub repo in the description, where you can explore and experiment with the code. In this video, we'll focus on math operations in assembly, not on downloading from GitHub or installing the Arduino compiler. If you want tutorials on those, let me know in the comments. To get started, open the Uno file, connect your Arduino board, and upload the code. This Arduino project connects to 4 AVR assembly files to perform basic math operations. The main Arduino sketch defines 2 numbers and sends them to functions for add, subtract, multiply, and divide. Each of these functions is written in low-level assembly to show how C++ and AVR can work together. The results are printed out in the serial monitor so users can see each calculation. The division function also includes error handling to avoid dividing by 0. It is a great example of combining Arduino with assembly for precise control and learning. There are many creative and functional ways to use the AVR functions in your projects. The add function takes 2 16-bit numbers, with the first stored in registers R24 and R25 and the second in R22 and R23. It uses the ADD instruction to add the low bytes, then ADC to add the high bytes along with any carry. The final 16-bit result remains in R24 and R25 for the return. The subtract function works with 2 16-bit numbers, the first in R24, R25 and the second in R22, R23. It subtracts the low bytes using SUB and the high bytes with SBC to include the borrow. In AVR assembly, a borrow happens when you subtract and the result goes below 0. Basically when you owe a value to complete the subtraction. The result is stored in R24 and R25 for immediate use. The multiply function uses only the low 8 bits of each number, with the first in R24 and the second in R22. These values are moved into R18 and R19, then multiplied using the MUL instruction, which places the 16-bit product in R0 and R1. The result is moved into R24 and R25, and R1 is cleared to follow GCC conventions. The divide function takes 2 8-bit numbers, the dividend in R24 and the divisor in R22. It first checks if the divisor is 0 using the TST instruction to test the value and BREQ to branch if it equals 0. If the divisor is 0, the function immediately loads the error value minus 9999 into R24, R25 in hexadecimal form as 0xD8F1 and returns. If division can proceed, the dividend is copied into R18 and the divisor into R19, leaving R24 and R25 initialized to 0 for the quotient. The code then enters a loop where it compares the current dividend with the divisor using CP. If the dividend is still greater than or equal to the divisor, it subtracts the divisor from the dividend, increments R24 as the quotient counter, and repeats. When the dividend is smaller than the divisor, the loop exits and the quotient is left in R24, with R25 containing the high byte if the result exceeds 8 bits. The remainder is not stored or returned. Thanks so much for watching. If you have any questions or thoughts about the video, feel free to drop them in the comments. I'd love to hear from you and help out. If you enjoyed this content, don't forget to hit that like button and subscribe so you don't miss out on future videos. Thanks again for your support, and see you next time.